And today's lecture is about spatial indexing and spatial access techniques. In the first part, I will discuss spatial indexing technique, and I hope you can now see my slides. If not, please shout. I hope it's all clear. All right. Okay, let's go ahead. So the series is called Spatial Access, and spatial access has two aspects: the indexing. And what does indexing mean? Okay, assume you look for a specific record or a set of records, and the index then tells you where to look in the computer memory for that record or sets of records. So for example, if you are looking for my name in a big database, then in that database it is wise to put an index on the table with all persons on the attribute name. And then if you look on my name, you will find me quickly. So that is an index. Clustering is related, and clustering is putting objects close together that are often selected in one query at the same time. And it happens quite often with spatial data because you hardly ever select a single object, but you often select a range of objects in a certain rectangle, your window. And then it's important that the objects are clustered. So the index would give you all the locations of these objects, but if they would be in very, very different places in the computer memory or on disk, then you would need to access many disk pages, and that would make the system really slow. And we did some benchmarking in the past, and we did some random sorting, put on the same index without clustering, and the time difference was orders of magnitude slower if there was no clustering. And so indexing, knowing where a record is one thing, but putting records close to each other that you use together is the second thing. Okay, now first the indexing part. Yeah, why is an index needed? Spatial data is often very large data and multidimensional. It can range from megabytes, gigabytes, terabytes, even petabytes. It can be 2D, 3D, ND. And yeah, for interactive applications, you want fast responses. So when you are panning or zooming, you want to go direct to that place on the map and have no delays. Okay, why can a normal index not be used, like the B tree? The B tree is based on the principle that you can sort things. For example, names can be sorted on alphabet. So Peter, the P is before Tom with the T. And so we can make this kind of sorting. And on top of that sorting, we can create a tree structure. But okay, is the location 3,5 x and y 3,5, is that before or after 2,7? You cannot really tell. Okay, you could look at the distance from the origin, but okay, then you get kind of circles around the origin which have the same distance. So on the circle there is still no ordering. So that does not help us a lot because there is no single way to sort or multidimensional data. The other techniques used, hashing for normal data, is also not so useful because that is used for exact match queries. Then it works well. For alphanumeric data, you have that a lot. Look for a person with a certain name or a certain number. But in GIS, we often ask for ranges, everything where the X is larger than 10 and smaller than 15, and Y is between 3 and 7. So it's not an exact query, exact match query, but it is a range query. And that is the most typical type of question. Not the only, but it is the most important one. Yeah, then you have the different geometry types, points, lines, regions in 2D. Maybe you can ask from time to time an exact match query. Does this point exist in your data set? And then please give me the attributes. But more often you ask a range because that corresponds to a window in a display. Sometimes there are other queries like the nearest neighbor. So you click on a certain location and you ask, okay, give me the 3 nearest neighbors or 5 nearest neighbors or single nearest neighbors. In general, the K nearest neighbors or K and N. Some index structures are suitable in any orientation, or they use another orientation than rectangular. And okay, this is not the same for the different indexing techniques, as you will see later on. Some of them, I will show them all in 2D, but some of them also work in 3D or higher. Some of the indexing techniques do partition a larger object, for example, a river or a big municipality, in multiple chunks. Others always keep the geometry as a single object and a single entry in the index. Some structures are dynamic. That means you can insert, delete, and update new data, and the structure still has a very good performance. Other structures are less dynamic, and when you keep on inserting or deleting or updating data in a certain manner, it can degenerate. Many of the spatial access methods are originally being proposed for outside the database, so that means in regular programming environments, in structures you can use in Python or in C++. But some of them are also very suitable in a database. And when you have them in a database, the benefit is that once you computed the index structure, it will always be remembered. And with a program, when you load a certain data set, you also have to recompute the index every time you load the data. Otherwise, or in a specific exception, you could also store the index, but then you also have to write the index. And that does not happen that often. Usually there are libraries to create such an index in the main memory of a program when you load data. Okay, when we analyze index performance, we can look at the theoretic worst case performance. So whatever data set I give, uniform distributed or not uniform distributed, and I insert the data and I do queries, what is the worst case performance in both insert time and in search time? And this is important because then you can guarantee, okay, whatever happens, however the data is distributed, I will always be able to guarantee this speed of loading or inserting data or querying data. In theory, the performance is on of the implemented structure can be sometimes different or even better than the theoretic worst case, because your data may not be worst case distributed, and then you get better performance even sometimes with irregular distributed data than what you predicted with the theoretic worst case. And what's also very important is that it is implementable. Many data structures that have been invented in the research are so complicated that it is often not implemented in a database. Okay, this is all talk at the meta level about spatial indexes. What can they do? 2D, 3D, what is their performance? This is one more slide on the metadata level, and that is what you could call a family overview of all kinds of index structures that have been designed, and not all in the context of a database, but in general. And you can see it has an old history. In 1966, there was the first article on using the Morton space filling curve to handle spatial data efficiently. In 1975, the KD tree was reported, and you see that once an idea has been launched or described in literature, people make variations on it. For example, the BSP tree was reported in 1980, or the B tree also in 1980. There is a relationship between the space filling curves and the quadtrees, the point quadtree and the region quadtree. I will explain that later. Okay, though hashing is used mainly for exact match queries, it has also some use in spatial data handling. But a very important category is what you find over here. That is the R-tree or range tree. And there are many variations on it. For example, the sphere tree. During my PhD research, I proposed this organization, but also the R+Tree and the R*Tree. And the last family I will point you to is the kind of grid file related structures. And from this one, we will have a look at what is called nowadays the field tree. Okay, as you saw from this already old family overview, many different spatial indexes do exist. However, few are implemented in a database, and you have not many options. And so in Postgres, you only have for the spatial index, only the GIST index, basically a kind of R-tree. Some other databases may give you also a quadtree, but that's basically it. And if you want to have an under-index structure, and then you have to develop it yourself inside the database, which is really tricky programming. Okay, a second remark is that some of the spatial index techniques are used in practice in combination with space filling curves. That will be explained in the second half of the lecture today. Also, this family overview is not complete. As I said, in my PhD research, I investigated quite a number of them, and the KD2B tree, the reactive tree, they are missing on the overview, and I'm quite sure they exist because I developed them. I will now present you 4 different families or representatives of the families in more detail. The Quadtree, a very well known one, the R+Tree, the KD tree, and the field tree. For the first 2 categories, I will also discuss some alternatives of the Quadtree and the R+Tree. Okay, the Quadtree, probably you have seen it before in one of the earlier courses. It's a generic term for all kinds of trees that are based on recursive division of space into 4 parts. So that usually means that you surround your area of interest, your domain, by a square. And then you keep on subdividing this domain until your object is completely covering that part of the domain, or you reach the bottom resolution. And in this example, I have as bottom resolution 3 levels, so I can split it 3 times. In blue, I have a line, and this line is kind of approximated with the highest resolution by these 4 cells in the Quadtree at the bottom level. And they are located over here at the bottom. And you can find them by traversing the tree. And so most of them are in this part, which is the northwest. So northwest, that is this branch. And then the northwest branch itself is subdivided into 4 parts. And it's then again in the northwest, sorry, and so this was the southwest, and then in the southwest you are in the northwest. So this is the southwest, and in the southwest you are in the northwest. So you have 4 quadrants: northeast, southeast, southwest, northwest. And they are labeled also as the 4 branches in the tree in this order. And that happens at every level in the same order. And so this blue line is represented by these 4 cells. Okay, perhaps a line is not a nice example, because the 4 cells look a bit different than the line, but okay, it's an approximation of the line. Let's have a look at the polygon. So here you have a polygon, this triangle polygon in this case. It's overlapping with the number of cells, and the cells that are now black are together representing the polygon. And what you see, in contrast to the line, is that you now can also have cells at higher levels, not only at the bottom level, but also at the 3rd level. And that means, for example, that the complete quadrant at a higher level is used to describe this polygon. I hope that is clear, and this is a kind of efficient way to describe that polygon. Of course, you could subdivide such a cell, but then all the children would also be black, indicating they belong to the polygon. So having a leaf node at a higher level is a kind of shortcut to avoid storing too many branches in the tree. And we are worried about these kind of things because spatial data is often a lot of data. Okay, that was a line and a polygon. being approximated by the cells of a quadtree. Now if we look at two other types of quadtree, first the point quadtree, and I have 6 points, A, B, C, D, E, and F, and I insert them in this order. First A, insert it over here, and A becomes the root of my tree, and it subdivides the domain into 4 parts, like a normal quadtree does. The difference now is that the location of A is used as the location where the splitting lines are being put. The second object is B, and B is located over here. That is to the northeast, and northeast is the first branch. So this object B is starting here in the tree. Okay, northeast, that is the first branch, and there is nothing initially when inserting only A and B, and the node B is created over here in the tree, and that means splitting the northeast quadrant into 4 more parts. These 4 branches represented. Then I get C, go in the tree. Okay, C is also to the northeast of A, so this branch, then check against B. C is also to the northeast of B, so that is this branch. So this is the order, and it's put over here, and it subdivides the space into 4 parts. Okay, object D, point D, go to the top of the tree. It is to the southeast, so that is the second branch below E. There is nothing else in the second branch, so D is put over here, directly below A, even if it was after C, that doesn't matter. And it splits this space over here into 4 parts. Okay, and so on when E and F arrive. Note that the structure is depending on the order. So if you would insert the points in a different order, you would get a different tree. But all these 3 help you to do a search. And I will switch to a pen now. And I will use a little different color. So assume I'm searching in this area. What I do is go with the box to the top of the tree. I will check for overlap with the northeast, this branch. There is no overlap, so I can forget about this branch completely. There are no candidates. I also check with the southeast. Yeah, there is overlap, so I have to check this. I check also with the southwest over here. No, there is no overlap. And I also check for overlap with the northwest. Okay, also no overlap, so I don't have to check these branches. So then I arrive at this level. And by the way, the blue box does not contain A, so A is not reported. Then I come at the second test over here. D is included, so I have to report point D as my answer. As you can see, it is overlapping with all the 4 branches, so I have to check them all. So all 4 of them have to be checked. And at the next level, I find indeed at the first branch E that is contained in the box. I have to also check the children below, but there are no children, so I'm ready here. Then I check the second branch that was indeed overlapping with the search box. I find F. F is not inside, but 2 children are inside. These 2, the west ones, the southwest and the northwest, these not, but these are overlapping, but they have no children. So there will be not any candidates over there. So in total, I report only D and E. And if you look at the map over here, that is correct. Okay, one last Quadtree type before a short break, a short 5 minutes break. The point region Quadtree, it's also from the Quadtree family, so also dividing space into 4 parts. This one is more to the original style of Quadtree, like subdividing space through the middle in both directions. I insert 6 objects, and I have a rule. In every quadrant or subquadrant, I can only store 1 object. So in the beginning, when there was only A, it would look like this. I'll draw a mini version of the rectangle over here, and A is inserted here. So no subdivision. And so the tree would look like it could hold A in the root. But then there comes a second object, object B over here. And I can only store 1 object in the tree node, in the node of a tree. So I have to split it. Okay, there's only one way to split in the normal PR Quadtree, and that is through the middle. So my simple single node as a tree becomes like this. And I get 4 children. And in the northeast, I have object B. Southeast, nothing. And in the southwest, I have object A. I can also draw little boxes around them to make them look fancy. Okay, this is repeated over and over again until you have inserted all the objects, and when you've done that, you end up with this kind of tree. Okay, why is this an index? Because it helps you with the searching. I will do one more example of searching. For example, I'm looking over here. This is my query region. Or let me make it nasty. This is my query region. So forget about this one. I go with my rectangle to the top of the tree. I check, okay, which nodes of the tree, which of the 4 nodes do you overlap with? Okay, in this case, 2 ones, the northwest and the northeast. So northeast is the first one, so I have to check this one. And the other one was the northwest, and it was this one. And the other ones, oh, I can forget about. So I can also forget about the northwest because there are no children. Yeah, there's empty over here. And then when I go to the northeast, you can see I have a splitting node, and I have to check with my query geometry all the 4 quadrants because it's overlapping with everything. So I have to check them all, but here is nothing, here is nothing. Here I find B, but B is outside, so I do not report B. And finally, when I check here, because also this quadrant is overlapping, I find object C. So my answer to find all the geometries in the green rectangle gives object C. Okay, it's time for a short break. If there are no questions, I will see you back in 5 minutes. That means 14:20, so 10 minutes before 2:30. See you in 5 minutes. Okay, welcome back. Let's continue with the indexing techniques, the spatial indexing techniques. Okay, we covered now the Quadtree family with a number of examples. Let's go to another family. Let's have a look at the R-tree with a number of variations, the R+Tree, R*Tree, and Quadtree. Okay, the R-tree works really different in organizing objects, spatial objects. It puts a minimum bounding rectangle for any type of objects. So it can be a line, a point, a region, does not matter for the R-tree. So for the point and the PR Quadtree, it's quite different, but by just abstracting to a box, the minimum bounding rectangle, the R-tree starts to work. And it tries to group all objects that are close to each other in leaf nodes that themselves also have a minimum bounding rectangle. So if you look at the group over, let me put on the pointer again. Group A over here that has 4 objects, D, E, F, and G. So A has a rectangle, but also D, E, F, and G have a rectangle, the real objects. And actually, the real objects may have different geometries in them. So G could be a line like this, or E could be a polygon like this. You don't know. Does not matter for the R-tree index. And the cool thing is that the R-tree is a dynamic structure. You can keep on deleting and inserting new objects. And it is guaranteed that the nodes will at least be half full. So here I don't have 2 free spaces, but we have for every node 4 options here. And that's called the branching factor. That's the general structure of the R-tree. So the nodes that have references to children and how many references they can have or how many objects they can store is called the branching factor. And the fact that the R-tree is dynamic under the inserting or deleting of objects is really nice, because it can guarantee kind of worst case performance. And what I did not tell you is the leaf nodes will always be at the same level. So here we have 2 levels, the top level and the bottom level. All leaf nodes are at the same level. So let's do a little example. So this is our R-tree again. There are some top level rectangles and some lower level rectangles corresponding to objects. Let's add 4 more objects, 1, 2, 3, and 4. And where should they go into the existing R-tree? So object 1, okay, that's easy. That fits directly into object 1, fits directly over here because there was a free slot. So I can store it over here, and not only because there's a free slot, I do not need to increase the size of A to cover object 1. So now object 2 is in the middle of object B, and so it fits here. Go to the second branch and put it over here. So easy peasy. not difficult. No extension of B to the rectangle and free slot, it fitted. Now I'm inserting object 3 over here. And as you see, it becomes really complicated. Object 3 does not fit in any of the existing rectangles, super rectangles, A, B, and C. It is closest to B, so I would like to store it in B over here. But B is already full. I can only store 4 things, and this would be thing number 5. You could say you could store it perhaps in C, but then the grouping, the spatial grouping is not taken care of. Because then if I would extend C to cover 3, it would be a super big rectangle. This new C, that's not good for the grouping. So, yeah, a problem. B is full, what can I do? Yeah, I can split B into 2 parts, B1 and B2. So I had 5 objects, and of these 5 objects, B1 gets 2 of them, the top 2, and B2 gets 3 of them, the bottom 2. And you see here B1 and over here B2. And instead of 1 node, B becomes now 2 nodes. I have 2 nodes for B. And that could be done because in the root node over here, I still had space for 1 additional free slot. And you see, after all these inserts, I'm still having all my leaf nodes on the same level. And I can insert quite a bit of them before getting into problems. Yeah, here you see also where the guarantee of the nodes will at least be half full. Because after a split of a 2 full node, at least one of the nodes, one of the 2 halves, will have a half full occupation, and the other one will have a half full plus 1 occupation, if you divide them well. So this is where this, let's go back, this at least half full guarantee is coming from in this insert strategy. Okay, now insert object number 4. So object 4 is over here in the upper left corner. Did go too fast. So here is the object 4. Would best fit in object A, so this branch, but A is already full, the same as B was full before, so I have 5 entries for A. Okay, I know the trick. I split A into A1 and A2, and this time A1 gets 3 children, D, 1 and 4, and A2 gets 2 children, F and G. I have an issue over here. At the root level, now all my entries are full with A, B1, B2, and C. B2 actually. And where to put A1? Okay, what is the trick when I have 1 entry too much? I split this guy over here. So watch. So now the root node is split into 2 root nodes, into X and Y. So X and Y. And X gets 3 children, A1, A2, and C. A1, A2, and C. And Y gets B1 and B2 in its children. And due to this insert, all the nodes, due to an insert of one object, all the leaf nodes did go from one level deeper. So first they were at 2 levels deep, now they are at 3 levels deep from the top. But it's all balanced. So when I'm looking for a certain object in a certain region, I know for sure I do not have to go deeper than these 3 levels. And the number of levels you go deep is an indication how fast your query can be responded. Okay, what you saw over here, for example, over here and over here, is that the rectangles can overlap a little bit. And that is not nice, because for a point query, you need to traverse multiple paths. And okay, for a range query, this perhaps not matter so much, but for a point query, you would like to be able to answer that in exactly the number of steps that corresponds to the depth of your tree. So the R+Tree says, okay, I do not create overlapping rectangles at the higher levels, but when I would need to have to do it, I have this object that is in the overlapping rectangles. I put them in both rectangles. So G is now partly in A and it's partly in B. It was a nice idea and it's good for point queries, but in the real world it is not an important gain, because the majority of queries are range queries, and for range queries or rectangle queries there is no gain. Difficult to understand directly, but it was discovered after serious testing with real data. Okay, there were some other variations on the R-tree. For example, the R+Tree that had a better insert and delete algorithm. By the way, I did not discuss delete algorithm yet, but you can read it in the paper that is in the reading assignment. But by having a little bit smarter delete and insert algorithm, it can be guaranteed that the nodes are fuller. And okay, when does a node not get full? That happens after a split, like over here. Then you have a bit of an empty node. So what is the R+Tree doing? It is not just looking at one sibling that is being split, but it is also looking at 1 or 2 more neighbors, that the whole cluster is locally reorganized. And then you divide the new empty nodes not in 2 new slots, but among multiple slots. And then the average population is getting about 30% more dense, and so less free slots. And that means also the data structure is smaller, the index is smaller, and it will be faster, because smaller means faster. When you can put the same data in a smaller index, then you can access that index more quickly. Okay, the techniques discussed so far, Quadtree, R+Tree, are axis aligned, so horizontal and vertical aligned. And in many map applications, you have some kind of display that shows the map in the direction you are walking or bicycling or driving with your car, called the head-up display. And when you are going in such a head-up display, and okay, let me draw it over here. It's the pen. Okay, it's nice if your query geometry is like this, that aligns well, but when it is rotated, these rotated rectangles really overlap a lot with the axis aligned rectangles. And so there's a kind of preference. It works best if the orientation is the same of the search rectangles and the rectangles you use for grouping, or the splitters you use in the Quadtree. But I thought, was it not better if you could have an index structure which has no preference for orientation? And I thought, okay, yeah, I can reuse the idea of the R-tree and make a kind of circle or sphere tree in 3D. And instead of bounding boxes, I take bounding circles and apply the same kind of rules. Have super circles that cover big objects, like over here, a number of big circles. Build the same tree structure. It worked. There's only one thing. It is super easy to compute the minimal bounding rectangle, and it is not so easy to compute the minimal bounding circle. Okay, think of some examples. You have some points that represent either a polyline or a polygon, but now we look at the points. Okay, if you are looking for the minimum bounding rectangle, you just look for the minimum x. And that is over here. You look for the maximum x, that is over here. The minimum I, that is over here. And the maximum x, that's over here. And so just look for x min, I min, and x max, I max. And that is just checking all the coordinates. But okay, what is the minimum bounding circle? And where is the center of the circle? How many points will be on the boundary? So looking at this scheme, I would say the center would be about here. These 3 points would be on the boundary, and that would give me a circle like this. Okay, I cannot draw so neat, but really draw sets of points and try to compute the minimum bounding circle. It is not easy, and you will discover that you were not the only person that had this question when you try to solve it. Already the old Greek had this problem, and they call this the Apollonius circle. And only about 30 years ago, an efficient algorithm was invented for this problem. So I implemented it, and it really worked well. And I had an orientation insensitive solution. It had some other benefits instead of the orientation. Okay, in 2D, for the minimum bounding rectangle, I need 4 numbers to describe them, x min, I min, x max, I max. For the minimum bounding circle, I just need 3 numbers, x center, I center, and the radius. That means more compact, and more compact is faster. But I also lose a little bit. On the average, the circles are a little bit bigger in area than rectangles. It depends on your data input, but on the average, the rectangles are a bit more compact, and that is a drawback for the sphere tree. Okay, I would say these are the 2 most important structures, Quadtree, R+Tree, also the ones you see most in reality being implemented. But let's have a look at 2 other structures, the KD tree and the fill tree. They are really easy now you understand the others, at least this one. The D tree, it's a binary tree, So the Quadtree is not a binary tree because it is splitting into 4 parts at every node, at every level. But KD tree does a split into 2 parts. And it does it by alternating splits in the horizontal and splits in the vertical direction. So similar to the point Quadtree, it depends on the order in which you insert the points. So assume point A is inserted first, so it becomes the root of the tree. There's a left space over here, and there's a right space that's over here, and perhaps my pointer is a bit small. So go back to the laser. So this is the right space, and this is the left space. This is the left space, this is the right space. After point A, I insert point B. It's on the right side, so it goes to the right branch. The point B is inserted, and it splits this subspace into 2 parts. A bottom part and a top part. Bottom part here and a top part here. Insert C is left of A, is on the top side of B, so it should be inserted over here, and so on. And so the insertion of points is kind of subdividing space, and you have alternating splits on the X and on the Y level. That is kind of nice, but it's also resulting into an unbalanced tree, and not all leaf nodes are at the same level as we had with the R-tree. This is kind of the same as with the Quadtree. But here it looks even worse because it's a binary tree and not a tree with, say, 4 options, 4 branches. Okay, this is not nice. These long branches, these deep levels in the tree are potentially slowing down search. So let's do something smarter. Do an adaptive KD tree, and that is, okay, sort the points in 1 dimension. First sort them in the X dimension, and then split more or less halfway. And in this case, because it's uneven, 2 on this side, 3 on this side. This is splitter number 1 in the X direction, this boundary. Then on the left side, sort the points on the Y dimension and split halfway. So that is over here, splitter number 2 in the Y dimension. Do the same for the other branch, split over here, also in the Y dimension, between these 3 points, halfway. Okay, C is to the top, and the other space is to the bottom, and this last bottom space is subdivided according to X, because you have alternating X, Y, X splits, and so on. So the benefit, it's more or less balanced tree, plus of min 1 at the bottom. That has to do with the number of points. However, it is not really dynamic. If I keep on inserting more and more points in a certain part of the space, if I would insert points here and more points here and more points here and more points here, the balancedness would be gone. It needs to know all input data in advance. And when you insert a lot of new data, it gets out of balance. And the only thing you can then do is do a recomputation of the index. So throw away the old index and compute it again. And then you have it balanced again. Okay, the last structure, the last index. And that is perhaps the most simple one, the most intuitive one, the ones we also do when we look on a paper map or in an atlas. You look for a certain city and you go to the index in the back and say, okay, look on page 50, and then it is in cell C5. Yeah, so C is the row and 5 is the column on that map. So in blue, we have a big grid. And so we could label them like the normal rows and columns on a map and put data over there. Okay, the drawback is that grids may not be equal full. Some cells may be full, other cells may be empty. Okay, what grid size should we use? So the field tree is a kind of adaptive grid that refines the grid in steps of 2. So starting from the most coarse grid, the second grid is having edge length halved, but also the origin is shifted. And why is that? The reason is, if you would be crossing a line of an important top-level grid, like a splitter, top-level splitter in the Quadtree, then you can never get off such a grid line. And by shifting the grids, maybe on another level, you can be included in the cell completely. So this is the thinking. So think back to the Quadtree, to the original Quadtree, and if you would have an object, a line or a polygon that is crossing the boundary of one of the top splitters, it will never get off that boundary because the boundary is on a fixed location. But if we switch the grid levels, the grids at different levels, then at one level the object may be crossing a boundary, but not at another level. And because of this property, and we have the ambition to store the objects in the finest possible grid, because that gives giving them best location information. And so try to store the object in the finest grid. And then we can prove that an object is never stored 2 levels above its own size. And so that is different to Quadtree. And so, okay, let's have a look at a number of examples. And so objects C, F, and G fit in the finest grid. And so here is F, and here is G, all lines, and C. C even fits in the green dashed grid, despite crossing another level grid, but it doesn't matter, it fits there, so it's stored over there. All the other objects cross green boundaries, the finest grid. Then the red dashed grid is the second level, and then there we can store object B that crossed before the green boundaries. We can also store object H that it also fits in a red cell. Then on the third level, we can store object E over here. And it was crossing the green and it was crossing the red grid, but it's not crossing the blue grid, so it can be stored. Some objects like A and D have to be stored in even higher level grids, bigger grids. A is not that big, and it managed to cross the green grids, the red grids, and the blue grid. But if we again would make the next grid level duplicating, and I'll depict it with a black line, so that would be somewhere over here, somewhere over here, and somewhere over here. Then it can not cross again. So that is this property. Okay, you can be unlucky a few times, but not 3 times. Then you really fit for sure in such a grid. That's a nice property. Okay, the way the field tree is used, that we actually give the cell in number, and empty cells are not stored, so they don't waste space, and this number will be encoded rather smart. That results in the spatial location code. There's the paper in the reading material. It's not only the field tree, but it's also the encoding of the grid cells according to a space filling curve. Okay, to conclude this first part on the spatial indexing, many different index techniques exist. Only a few are available in the database. For example, in Postgres and PostGIS, you have the GIST index, which is basically a kind of R+Tree. There is a difference between one or another technique, but the difference in query performance or in load performance is 10%, 20%, sometimes extreme case 50%. But the biggest difference is in using an index or not using it at all. That will give you orders of magnitude, 1, 2, 3 orders of magnitude. So 100 times faster or 1,000 times faster is not strange at all. Okay, now I discussed only the indexing part. You will also learn about the clustering, because indexing is pointing to objects you need. Clustering is making sure these objects you need are close together. I presented mainly everything in 2D because that is easier to draw, but nearly all of the techniques also do work in 3D or even in 4D or 5D, but then they are really hard to imagine. But in 3D, that works. So you can have a Quadtree in 3D, then it is not called a Quadtree anymore, but an octree. It splits the space into not 4 parts, but 8 parts. It splits on X, it splits on Y, giving the 4 options. And then it splits again these 4 options also in the Z direction, giving 8 options in total in 3D space. Something similar is also possible for R+Tree. R+Tree is also used a lot for indexing 3D geometries. But there is no reason why we could not generalize it to even higher dimensions. Okay, thanks. This ends the first part. Let's have a short break again and see you back at 15:00, so exactly through 3 o'clock. And I see some questions in the chat, so I will address them. Does the order of the leaf matter? In principle, I used a fixed order to explain what is northeast and southwest, to match the scene, the map, with the objects and the tree structure and the subdividing of the space. But for performance, it doesn't matter. But in implementing, you have a fixed order. Then a second question, is there always space for 4 values in one region? Or are there other configurations as well? Okay, very good questions. For the R tree, I used a branching factor, or also called fan out, of 4. In real implementations, they often use much higher values, like 100 objects in one node. So that means with a really big data set of million objects, you still only have 3 or 4 levels. Why is that? Because you can store these 100 nodes easy on one disk page, and one disk page is an efficient unit to get into the memory of a computer from your memory, from your disk, and that is efficient. And your CPU is very fast, so you can do then easily 100 overlap checks to see, okay, which children do need to be accessed. So the 4 was more an example to show the principle, and I was too lazy to draw 100 children, and it would also not fit on the slides. Okay, another question. When inserting new data, is the result unique? When insert 4, can A1 only contain 4 and 1? Okay, when you start inserting objects, what you try to do is find the parent rectangle at all levels, starting at the top level, at the biggest rectangles, that needs the least extension. So if a new object completely fits in one of the big rectangles, then you go there. If you need to extend a little bit, and if you need to extend the other a little bit more, a rectangle, then you go for the one that needs the least extension. It could also be that the super big rectangles already have a little bit of overlap, and that the new object is in the middle of the overlap, and then it's kind of arbitrary which you choose, and probably it is best then to choose which has already the fewest children and go to that branch to make them more populated, better balanced. So there are different situations, but the algorithm in a sense is deterministic, going for the higher level rectangles in the hierarchy, and that needs every time the least extension. I hope this answers the question. Okay, okay, Simon, for sure. I now see that you are referring in the first question to the R-tree. There, it does not matter at all. And it's totally arbitrary, the order. It has no meaning. In the Quadtree, I gave it some meaning to make this mapping between northwest and northeast and southwest and southeast to have a systematic depiction. But in the R-tree, it has really no meaning. It is just convenient to use the same ordering after an insert, so you can compare it 3 before and 3 after the insert. Okay, I still have a 1 minute break to get a little bit of tea, and then in 1 or 2 minutes we start with the last part of the lecture, the space filling curves. Okay, that was rather a short break, but we still have some material to cover. And to see if you are all awake, I would like to do another poll on the spatial index. And here you see 2 questions. So wake up, wake up, wake up. Think back. Okay, which of the following index structure is balanced? And there are more options possible for being balanced. So point, Quadtree, R+Tree, PR, Quadtree, KD3, Spatial, adaptive KD3. So all possible to be balanced or not. And the second question is the KD3 or the adaptive KD3 dynamic or not? Okay, I see votes coming in. Okay, I'll wait a few more seconds because now it is going well with the thinking. I want to have at least 15 votes in. And we are at vote number 11, 13, good. Okay, one more vote. Yeah, 16. I will end now the poll and I will share the results. Okay, the favorite one for being balanced is the R+Tree, and that's completely correct. It's a balanced structure. It's always at the same level. But also, the Spatial was balanced. The Spatial is basically a kind of R+Tree, but then instead of rectangles, you use circles or spheres in 3D. Rectangles in 2D. Spheres, circles in 2D. So it is as balanced as the R+Tree. Also, the adaptive KD3 is balanced. So also this was scored rather well, and that is correct. And the others, the KD3, yeah, not balanced, I'm sorry. Even if 6 people think so, on the exam, this will not help you. KD3 not balanced, point Quadtree not balanced, and point region Quadtree not balanced. So balanced R+Tree, Spatial, adaptive KD3. And the second question, which structure is dynamic? Yeah, adaptive KD3 or the KD3. The adaptive KD3 will lose its good structure, it is balanced structure when inserting objects. The KD3 was not balanced anyhow from the beginning, so you can keep on inserting and it will always remain a very good KD3. Good. It remains a KD3, and the adaptive KD3 will really use the property of being balanced. So the KD3 would be considered dynamic and adaptive KD3 not. So only a few, 4 had the right answer here. Actually, my favorite example of a dynamic structure is the R+Tree, because it is really remaining so nice balanced. Okay, let's now go to the second. Stop this. Yeah, there it is. Now go to the second part on the space filling curves, the second and the last part. And yeah, the space filling curves together, with the indexes and make up spatial access, because space filling curves can help you with clustering. What is a space filling curve and why are they so important for managing spatial data? So the mathematical definition, it is an ordering or a numbering of the cells in KD, so 2D cells or 3D cells, grids, all little cubes or squares. These multidimensional things, to map them to a 1D number in a bijective mapping. Okay, what does it mean? That means I can give you my grid cell, the column number 2, row number 5, and I get back a number, for example, 23. That is the one direction, but I can also go back in the other direction when I get the number 23 of the ordering on the space filling curve. I can figure out, okay, which row and column was it, so which cell was it. So that's bijective, being able to go in both directions, bijective. It has a long history, okay, not so long as the Apollonius circle, going back to the Greek days, but the space filling curves were investigated by mathematicians already for, say, more than 100 years ago. For example, Peano and Hilbert were studying them. The question was basically, a line is a one-dimensional primitive. Remember, a point is zero-dimensional, a line is one-dimensional, an area is two-dimensional, volume is 3D, but okay. A line, a one-dimensional thing, can you cover the complete 2D space? Some mathematicians say, okay, not possible. Others say, yeah, okay, it is possible if we have a very special line and we refine it until infinite, then we can prove we will visit any point in the 2D space with just a 1D line. Okay, the cells we use in our examples, in the practical examples, are usually squares in 2D or cubes in 3D, but others do exist. I will not show them in this lecture, but they do exist and can be used in combination with space filling curves. Okay, here you see a kind of an overview of 8 different space filling curves. Assume you have a world of 4 by 4 or 16 cells, and you number them from 0 to 15, and that can be done according to the row order. So first row 1, 0, 1, 2, 3, then go to row 1, 4, 5, 6, 7, go to row 2, 8, 9, 10, 11, go to the last row, number 3, 12, 13, 14, 15. Okay, this is called the row. There's a nasty thing. We jump back to the beginning of the row and then number them again. And to avoid the jumps, so this is a rather long jump in space. The row prime is going like a snake. Between the odd and even rows, it goes on different sides to the next level. Here it goes on the high side to the next level. Here it goes on the low side to the next level. The spiral is kind of, okay, you go to the outer boundary of your domain and start walking on that until you are completing your round, and then you are going to the cells to the next outer boundary, and in this case there are only kind of 2 rings to be made, and you number all the cells with these numbers from 0 to 15. It's always from 0 to 15 if you have a 4 by 4 world. Morton is doing it by making these small kind of N shapes. Look, here is a small N. repeated over here, and also over here. And also then the 4 parts are connected like this N. And that also gives an ordering from 0 to 15. The gray makes some other jumps. Here's a long jump, and here's a long jump. Here is also a long jump. That's also not so nice. The Hilbert curve is also a nice curve that does not make the long jumps. And also the diagonal or contour ordering, like a kind of scan, similar to the row and row prime, but then not going horizontal, but going diagonal. And the last one, I'll also go into more detail, is yeah, the units are not squares, but here the units are triangles. And of course, 2 triangles make a square, but or two triangles can make a square, in some cases, not always. This is of ordering these triangles. Yeah, nice space-filling curve manner. Okay, for row prime, spiral, contour, the construction is rather easy. Just follow the skin line or the diagonal or the spiral. Piano is funny and interesting. I already mentioned a little bit this N shape. And actually what is happening is that the N shape is copied from one level to the next level. So it's put from, this is the first level of refinement, and here is the second level. And so from the previous level, I copy here, I copy there, I copy there, and I copy there. And I connect then the 4 copies into this order. So this one is connected to this one. This is the last of this one. This is the first of this one. This is the last of this one to the first of this one. This is N order. And this is the last of this one connecting to the first of the top friend, and gives you this shape. There's an alternative which will be explained soon, and that is really, really cool. The binary or the reflected binary gray is using some kind of reflection, alternating over the I and the X lines. Okay, compute the piano key, but again, if you look, I'm using a pen. If you look to the ends over here, this is an N of the previous level, and one over here, and one over here, and the one over here. It's now getting messy, but they are connected in this order. See the big N over here, and because this guy is the last one of the first part, and this is the first one of the next part, and this is connected. And this one is the last of the second part, and this one at the bottom is the last of the third part. They are connected, and the same. So that is this diagonal of the big N, and the third part connecting to the fourth part. This is the last of the third part. This is the first of the fourth part, and this is then the connection. So that gives you a curve of not 4 by 4, but 8 by 8, or from 0 to 63. But I said, okay, you can do it by bitwise interleaving. And what is bitwise interleaving? Okay, we use decimal numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. But actually in the computer, these are stored as bit patterns. And here you see 0 is if I use 3 bits, 0, 0, 0, 1 is 0, 0, 1, 2 is 0, 1, 0, 3 is 0, 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, and 7 is 1, 1, 1. And of course, that is also true for the y. So if I take an arbitrary point, say over here, then I know the x is 6 or 0, oh sorry, 1, 1, 0. And I know the y is 7. That means 1, 1, 1. This is the y. Then I'm gonna do bitwise interleaving. So I take a bit from the x, whoopee. I take a bit from the y, whoopee. I take a bit from the x, the second one goes here. I take a bit again from the y, that goes here. Take the last bit from the x, that is going here. And I take a last bit from the I, and that is going here. I get another number. I get 1, 1, 1, 1, 0, 1. And actually, in a decimal number, that is 61. I really hope you know binary numbers and do the conversion between binary and decimal. Okay, let's do another example. I use now the point over here. The x is 1 and the y is 2. So x is 1, that means 0, 0, 1. I is 2. 0, 1, 0. Bitwise interleaving. 0, 0, 0, 1, 1, 0. And actually that is 6. So is this not great? Instead of this whole complicated copying stuff, I can do a very simple computation, especially with computers that like everything. Yeah, for them binary numbers is the best taste there is. They like it better than text. They like it better than decimal numbers. So they are very good at this kind of computation, and it's very fast. And so we give it a coordinate, and it will compute super fast the piano key. Note, there is a synonym, piano key, Morton key, Z order. They are all the same, but they're synonyms. This is the other method. I will not spend so much time on it. It is less elegant, but okay, it is used from time to time. And what is also not so nice over here, that it is having also jumps over longer distances. By the way, that was also the case for the Morton key, or the also having the longer jumps. Okay, let's have a look at this elegant curve, the Hilbert curve. So we have the basic element. This is a kind of arch here at the bottom. So position 0, 1, 2, and 3. 1, 2, and 3. So we take a copy of the original. We put it at these 4 places, here, 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 and here. But at position 0, so this is position 0, this is position 0, we rotate it negatively. And that means clockwise. So with the clock. So that is what mathematicians call negative rotation. And at position 3, this is position 3 over here, we locate it, we rotate it positive, meaning counterclockwise in the other direction. So let's take this little arch and rotate it counterclockwise. So we have then 4 arches, we can connect them, and the last point of the first arch can be connected to the first point of the second arch. The last point of the second arch can be connected to the first point of the third arch. And the last point of the third arch can be connected to the first point of the last arch. Okay, then we do it again. Same procedure. We copy this whole thing to the 4 positions. So here, here, this position, here, and also here. The top 2 are okay, at positions 2 and 3, but at position 0 and at position 3 you rotate. So well, this is the orientation to rotate at the first position, clockwise or negative, and over here you rotate it in the different direction, positive or counterclockwise. And then to construct the whole curve, so the last point of the first curve, that is this one, is connected to the first point of the second curve. Walk home. Then we add the last point of the second curve that is connected to the first point of the third curve. Walk on. And we are at the last point of the third curve, and that is then connected to the first point of the last curve, curve number 4. Here we are at the end of the curve. So we can number all the 8 by 8 cells or 64 cells from 0 to 63. Really nice curve, and no long jumps. But what is not nice? What is not nice is that when I double the resolution of the curve, points get a different number. For example, the point over here has now number 3. 0, 1, 2, 3, that's the third point. But the same point in the second level curve is now number 1, so 0, 1. And in the third iteration, it is number 3 again. So there's a kind of instability in the numbers a cell have. So their location is not changed, but somehow their numbers are being changing when the resolution is doubled. Okay, this is one of the observations. And that actually this was the last observation. So is a curve stable? The Hilbert curve we last saw is not stable. Look at this point. The key values, the numbers, are changing when doubling or increasing the resolution. Okay, some other characteristics. Is a curve continuous? Okay, so if I look at 2 consecutive keys, are they corresponding to neighbors, 4 neighbors? Or do there not occur long jumps? And so the Hilbert curve is continuous. The Morton curve is not continuous because it makes these long jumps. Rho is not continuous because it makes long jumps, going from this like this. Not continuous. Rho prime is okay. Okay, that is no problem. Because neighbor cells have the next key value. So next key value here is also neighbor. Next key value here is not a neighbor, of this cell. It's far apart. Okay, no jumps. Quadrant recursive. Yeah, Morton, Hilbert, quadrant recursive. Row prime, spiral, not. Monatomic. For every fixed x, the values of y are changing monotomically. Okay, row prime are monatomic. Okay, let's look somewhere over here. This was 0, 1, this is number 2. But at these points, they are ordered in this way in the curve, and the I is only increasing. If we look back at the Hilbert curve, is it monatomic? For example, look over here. Oh, you can also already look over here. Okay, let's look over here now. Let's use a new color for the focus. Look over here. Zoop. I is going up. Okay, no problem. I is going up. So I can let me look up with an angle. Going here. Okay, I'm at complete other x. So not important. Not important. Okay, I is going down. Okay, and here it is. Again down. And so on one x location, I have both up and down going directions in the y dimension. So that is not monatomic. So row is monatomic and row prime is monatomic. Yeah, so these are a number of characteristics of the curves. Okay, there is an improved version of the Hilbert curve that gets rid of the problem with the non-stable numbers. So this last point here. So normally Hilbert is not stable, but the alternative Hilbert is stable. And how it works is, okay, you take the base curve and then you reflect near the endpoint. So this is the endpoint here, number 3. And you will reflect over here and you mirror it over here. And then after the mirroring, you will connect it like this. And what you will do after the mirroring, you will rotate the added part, or you will mirror in a diagonal. That's a better term. You will mirror the added part. So this was added. And you mirrored it in a diagonal. And then you get this part. And in this new part, this point number 7 is the last point. And then you duplicate it again by mirroring near the endpoint. And that is now a horizontal mirror after the vertical mirror. And you get the second level of the curve. So this is the first step. Mirror near the endpoint, double the curve. Step 2, do a diagonal reflection of the new part. Step 3, mirror again near the endpoint. And then you have one recursion added. Look now, this point over here has number 3. So x is 1 and I is 0. This point is now number 3. And here it is also number 3, like it was over here. And that can be done many times. And so this exactly the same recipe is also done for the second recursion or iteration. And so you double by mirroring, near the endpoint. So this is the endpoint. This part is being added, but it is being mirrored by this diagonal. Then you get this new shape. And okay, why do you mirror? You mirror because you want to have the point at a place where you connect, where you double. So I'm now using this range in the X, and I want to double it, and I want to go in this direction. So it's always nice to have it at the same side, at the high side. And then the last part is doubling by plane mirroring, and then you get the second refinement. And look again at this point, but also all other points of the original curve keep their initial number. Okay, looking at the time, it is going really quick. I will discuss the last important topic, and that is the curve metrics. So the total length of the curve, the different sizes of the units in the curve, the average distance of neighbors, and the average maximum distance of neighbors. These are all possible characteristics. And I take the average because there are many options depending on where in the domain you look for the neighbors. Therefore, it's good to take the average. A bit disappointing result is that the average distance of the 4 neighbor cells, so the cell above, below, and left and right to you, on an n by n grid is n+1 divided by 2 for many different orderings. And so the average distance is about the same for many orderings. But there are other important criteria that are not the same. For example, the Manhattan distance. So you look at, again, at a point, and you do that for all the points, and then you take the average, but you look first for one point. And we have now the cell size of 8 by 8, so 64 positions. And then this metric says, okay, go back 4 in the curve and go back forward in the curve, and then compute the Manhattan distance. So Manhattan distance from this point to this point is 1. From this point to this point is 2. From this point to this point is 1. From this point to this point is 2. So the maximum at this side is 2. And then at this side, the distance from this point to this point is 1, 2, 3, 4. From this point to this point is 3. So 1, 2, 3, and so on. And this is the one who's most far away in Manhattan distance. 1, 2, 3, 4, 5 units away. So in total, the Manhattan distance is 5 on this piano curve from the key neighbors. If I look here at the 4 key neighbors to the left and the 4 key neighbors to the right, then the maximum Manhattan distance is 3. So that's lower, and that's better. And we see that also in this curve, guys over here, Van Oosthuizen and Roseman, have done it for all combinations up to 16 by 16 grid. And you see that on a Hilbert grid, your 4 neighbors to the left, or in this case, the 8 neighbors to the left and 8 neighbors to the right, are closer than in Manhattan distance than on the piano curve. Similar criteria is, okay, I'm doing a rectangle selection on a grid, and I want to find all the points. How many parts of the curve do I pass? So here you see the rectangle, and it's the same rectangle. And I pass it once over here, then I going outside, I enter it again, second part, outside, I enter it again, 3 parts. So 3 ranges of the curve to cover this rectangle. For the Hilbert curve, I enter it here, 1 part, I enter it here, second part, and I'm done. So Hilbert has a lower value, meaning I need to access less parts, which is more efficient. So Hilbert is more efficient than Peano over here. So this is not a way to indicate that Hilbert is a good technique. Okay, the use of the curves are used for clustering. If I put the points in the way they are in the key, in the memory of the computer, then that gives me some kind of spatial clustering, especially the Hilbert and the Morton curves. Yeah, there are also other applications. For example, shortest path computation. There is a famous example of the Sierpinski curve, and if you connect the points in order of the Sierpinski curve, you can solve the traveling salesman problem in a very competitive manner. And what is the Sierpinski curve? Okay, that is this triangle-based thing, and I have given the triangles an orientation. One corner has a, say, kind of a red color, and I connect the triangles from low to high, and I split, and I make a low part and a high part. And every time I split through the diagonal of the triangle. And when I connect them from low to high, I get this ordering, and it's really like the Hilbert and also a little bit the Peano curve. Really nice artwork. So this was the application and how it was used. So they helped me to map ND data into 1D, and then I can use a normal 1D technique again. They are used in combination, for example, with the R+Tree. For example, then the center of the box of the R+Tree is the ordering of the R+Tree nodes in the computer memory. And not only for spatial indexing, but also for other applications, they are used. For example, the Sierpinski curve for a traveling salesman. And okay, this paper showed that application, and it was really, yeah, this is very fast in computing analog end time, and it was very competitive compared to the other earlier known solutions. It does work in many other situations, not only from 2D to a 1D mapping, but also from even 3D or 4D data. Oracle uses this a lot in what is called the HH code, hyperhelical code. It is for points and not so good for the polylines and the polygons. Okay. And the idea is the clustering. Put the data in the right order in the memory of the computer in a way that you can retrieve it fast. Okay, I said you have the index, like this statement in PostGIS. I create index using gist. That does not give you the clustering, but when you created this index, and after that, and you insert the data. And after that, you will sort the table. That gives you a clustering, because then the actual data is in the right order as it is in the index. In this case, it is not an SFC order, like in the Hilbert R+Tree, but it is cluster data. Drawback in Postgres, it is not dynamic, so you need to do a kind of periodic reclustering. Okay, to conclude, spatial curves have a long history, even before computers existed. Many curves existed, they have different properties. In reality, we see a lot of applications of the Hilbert and the Morton keys, for example, in the Hilbert R+Tree or in the spatial location code, and other applications. And they are also heavily used to organize point clouds, and that will be explained in the point cloud lecture. I will now stop sharing my screen. I will quickly launch my last poll to see if you are still there. Okay, so 2 quick questions to end the lecture of today about spatial and curves. So if I give you a key value, a Morton key value on a 4x4 grid or on an 8x8 grid, is it then possible to compute back the ND location, so the row and the column? Yes or no? First question. And okay, second question, nearly literal from the slides. Which of the different techniques is spatial and curves is quadrant recursive? Row, piano, spiral, Hilbert, contour diagonal. Okay, it's the end of the lecture, so I'm happy after receiving 12 answers. Yeah, okay, nearly there. We are at 10. Oh, we are at 14. I'll end the polling. The others need too much think time. Let's have a look at the answers. Is it possible, given the SFC key, to compute the location? Yeah, true. And why is that? Because it's bijective. You can go in both directions, from the location to the key, but also from the key back to the location. Only one person did think that it was not possible. It is. Second question, which ones are quadrant recursive? Row, no, very good. Piano, yes, also very good. Spiral, no, okay, 2 errors. Hilbert, very good. Quadrant recursive, correct. Contour, the diagonals, no, not quadrant recursive, so 3 errors. Well done. And I see one last question. Yeah, I always assumed that was already the case with the Quadtree, but now especially with the spatial and curves, that I have a square domain. And perhaps that's not the case. For example, if my country is called Russia or Chile, then that is not true. However, to make these methods work, we have to put a square around it. It's annoying, but the answer is yes, you have to put a square around it, and then the method does work. Only in some parts of the square, there will be no data, and these SFC numbers are not used. There are tricks to work around, but these tricks are not so elegant. One trick is stretching your data. For example, make Chile a bit fatter, more fat, by multiplying the x by a factor 10 compared to the y, but it is not nice. And then you are using this whole domain, the whole square. Okay, thanks for your attention. We are a bit over time, 15 minutes, so I'll now end the lecture. I will not be there at the lab this week, Wednesday. It's overlapping with the GIMA midterms, but both Wilco and Marianne will be there. So enjoy your lab with indexing, where you will load a bit more data and see the effects of the index.